Hello there. Recall that in a previous video, we defined informally what limits are. So informally, the limit of f of x as x approaches a is L means that f gets closer and closer to L as x gets closer and closer to a. In this video, we'll define formally what limits are. More specifically, we'll try to explain in mathematical terms what we mean by closer and closer. So to start, let's have this illustration. So we consider the function 3x minus 2, and we take note that clearly the limit of f of x as x approaches 1 is equal to 1. So we obtain this since we know that in evaluating limits, when we evaluate limits of this form, so we won't have any complications, we just plug in 1 out here. So we'll have 3 times 1 minus 2, and this will give us 3 minus 2 or simply 1. That's how we obtain this limit. But take note that in limits, we are dealing with values close to a certain value. In this case, we're dealing with only close to 1 and not exactly at 1. In here, we're dealing with x values close to 1 but not exactly at 1. So given this idea, let's try to consider inequalities. More specifically, let's try to consider bounds for our values. In this case, let's have f of x between 0 and 2. So technically, this is like f of x between 1 minus 1 and 1 plus 1. Since we know that we're dealing with f of x to be at 1 out here. So if it's quite confusing now, I hope that it gets better later on when we continue with this illustration. So the question here is that when will we have f of x between 0 and 2? Or what this means is that for what values of x will this hold? Well, let's try to solve that one. So basically, we replace f of x out here with 3x minus 2. So we'll have this, add to both sides, and we get 3x between 2 and 4. Lastly, we divide 3 both sides in all parts of the inequality, and we get 2/3 and 4/3 as the bounds. Or in decimals, this is x between 0.67 and 1.33. So essentially, if the values of x are within this interval, we'll get f of x between 0 and 2. So that's the idea behind this. So these values are close to 1 to represent this, while this one out here are values close to 1 to represent this. Now let's have this next one. So basically, we try to make the bounds smaller. So this is like 1 minus 1/2 this time, and this one is 1 plus 1/2. So it's now smaller compared to the first one. And let's try to do the same process. When will we obtain this inequality? Or for what values of x will this inequality hold? So we just plugged in 3x minus 2 in this inequality. So we'll have this. Do the same steps as in the first one. Add 2. We get this. Divide 3. And we get this. Or in decimals, this is around 0.83 for the lower bound and 1.17 for the upper bound. So again, these are values. This interval contains values close to 1. In fact, it is closer to 1 compared to the first one. this out here is also closer compared to 1. So now, let's have this last one. So we have f of x between 0.9 and 1.1. So in here, this one is already very, very close to 1. Since this is just 1 minus 0.1 and this is just 1 plus 0.1. So for what values of x will this inequality hold? So we just plug in again, 3x minus 2 in the f of x. Add 2, we get this, divide 3, and we obtain this. So we have x between 0.97 and 1.033. So clearly this interval out here is closer to 1 compared to the 2. So again, we're representing this part out here. And for this other one, which is also close to 1, we are representing this. So I hope you don't confuse that one, since we are dealing with x approaching 1 and f of x approaching 1. So there. Now let's try to generalize this idea. Let's first let epsilon, so this is a Greek letter, let epsilon be greater than 0, or let epsilon be a positive real number. Then we know that, or in general, we have f of x between 1 minus epsilon and 1 plus epsilon. So essentially, this is like this part. We have f of x between 1 minus 1 and 1 plus 1. This part, we have 1 minus 1 half and 1 plus 1 half. And this one, we have 1 minus 0.1 out here and 1 plus 0. So it's like the epsilon out here is equal to 1. The epsilon out here is equal to 1 half. And the epsilon out here is equal to 0.1. Clearly in all of these are all greater than 0, or positive real numbers. Now given this, take note that if we subtract 1 both sides, we'll get epsilon. So f of x minus 1 is between negative epsilon and epsilon. Or in absolute values, this is absolute value of f of x minus 1 is less than epsilon. So take note of this one. Moreover, given this, how do we obtain x? Well, like in how we did in the examples, we just plug in this function out here. So we'll have this. And take note that by similar steps, so adding 2, then dividing 3 afterwards, we'll obtain this. Or in absolute value terms, this is the same as this. So essentially what we did here is we subtract 1 both sides, so we'll have this there, and then this just equals this. But take note that an important thing here is that the absolute value of x minus 1 rather must be greater than 0. So it can't be equal to 0, since if absolute value of x minus 1 is equal to 0, then we have x to be equal to 1. Which we know that isn't what we want here, since we want values close to 1, but not exactly at it. So this condition out here is important. And now let's use these two. Oops, I forgot. First, let's denote epsilon over 3 out here to be equal to delta. So that is something important later on when we define what limits are formally. So we'll use these two outcomes in illustrating the given in a graph. So let's have a graph out here. And we know that the limit as x approaches 1, so we have here the x-axis and the y-axis. So let's fix this one. So the limit as x approaches 1 is equal to 1. So it's presented by this. And let's try to illustrate what happens here in the absolute value of f of x minus 1 is less than epsilon, or this part out here. So we have this. So we have 1 minus epsilon and 1 plus epsilon out here. So essentially, this is the 1. We just add epsilon out here up and epsilon out here down. So basically, it serves as like a distance, a measure of distance in this case. And we do the same for this delta out here. So we know that here, if we replace epsilon over 3 with delta, we have 1 minus delta here and 1 plus delta. So for this x part out here, we have this. Now essentially, since we are trying to get the limit, what we want to do is we want to try and shrink and minimize this distance out here. So when we minimize that one, this goes here, this goes here, this goes here, and this goes here. So that happens when when epsilon approaches 0. Again, we can't have epsilon equal 0, since if epsilon is equal to 0, then we are referring to this part out here already. But again, we're dealing with limits. So limits are close to it, but not exactly at it. So we'll achieve this if epsilon approaches 0. So as epsilon goes to 0, take note that the absolute value of f of x minus 1 less than epsilon means that f of x approaches 1. Since if this goes to 0, then these two must be very, very close to one another, or the same. Since if they are the same, this becomes 0, which satisfies the equation. But then again, we're not dealing with equalities out here. So instead of using equal out here, oops, wait a second. I don't think, oops, there. Okay, sorry for that interruption. My device is quite slow in some cases. So going back, so that's why we deal with f of x goes to 1 instead of f of x equals 1. Moreover, we know that we obtain this one, like in our examples, we obtain this inequality if we choose the x value out here to be this part, or in other words, this one. That's why we have this. And take note that since we're dealing with epsilon approaching 0, we have as epsilon goes to 0, we also know that x goes to 1. Since if this one out here, as epsilon goes to 0, this one becomes 0. And similar to our idea in the first one, since we can't have this two to be equal, since if these two are equal, then this becomes 0, which is invalid, since we know that this one cannot be 0. So we're just dealing with x going to 0, but not equal to it. So technically, that is the idea in limits. It's kind of technical, since we're trying to refrain from using the equal sign, and we're using arrows instead, since we're dealing with values approaching a certain value, but not exactly at it. But technically, this is the idea in getting closer and closer. It's like having this Epsilon-Delta definition and minimizing the epsilon, but not exactly equal to 0, so that it gets closer to this limit out here. So I hope you got that one. If not, then yeah, feel free to comment down below the parts that were quite confusing, and I will try my best to explain. But given that, let us now formally define what limits are. So the limit of f of x as x approaches a is L. So notation, we know that this one is the same as this out here is L. If and only if, so this acronym out here refers to if and only if. If and only if for all epsilon greater than 0, there exists delta greater than 0, such that if x minus a is between 0 and delta, then f of x minus L is less than epsilon. So as you can see, it's really quite technical. That's why when we first introduce limits, we just focus on informal definition, and more importantly on its intuitive idea. Just to take note again, this out here refers to for all. So these are math symbols that is probably introduced more on when you talk about proving certain things. So it's quite higher math already. So for all out here, and this one out here refers to there exists. So basically, if for all, when we say for all, this applies to all numbers. And when we say there exists, we can choose a certain value for this one. Like in our example, we choose the value of delta, which we have to be epsilon over 3. That's in our illustration above. And again, this one out here is the important part. Out here, you can forget everything in this wordings. Just don't forget these two. And given this two, the next question now is, how do we apply this formal definition in getting limits or proving that a certain value is indeed the limit? Well, that is something that we'll be discussing in the next video, since this video is already quite lengthy and quite technical. So you can stop here for a while so that you can digest first the material, and if you don't quite understand it, you can again comment down below or search for other references, since I acknowledge that there are some things that I might not be able to explain the best to certain audience. So yeah, I hope you enjoyed and learned a lot from this video. So yeah, that's it, and that is all for this video.